Hello everyone, my name is Katie Hardister, and today we're going to be going over Chapter 8, which is Algebraic Reasoning, Graphing, and Connections with Geometry. So we can jump on in. So for our first equation here, on our homework we were asked to match the graph to the scenario given. So we were given a list of different scenarios, and these were the graphs that were given to us. So at that point, what we did was we used algebraic reasoning, or just process of elimination, to decide which graphs went with each scenario best. So these are the graphs that I chose for the scenarios that were given. So the first one reads, explain and label a graph to correlate with the function of the amount of gas in a gas tank when a driver refills the tank on a drive across the country. So for that, first of all, I'd like to say anytime that we give students any kind of word problems, I always, and even for myself, encourage to underline, draw a squiggly line, something to kind of pull out that important information that is given. So for this equation, we're given, a couple important different things. What we're wanting to know is, we end up wanting to know, the gallons of gas that were used and the distance in miles that we drove. So anytime that you have a graph, you always have to label it. So that's what I'm going to do for the next couple of scenarios, is show how I would label these. So for this one, like I said, I would say that this is the distance in miles, and I'll show why as well in just a moment. Distance in miles, and I would say that this is the gallons of gas, and this is going to be gallons of gas used. If I could just write here, gallons of gas. So this, of course, is our X, and this is our Y. This is, of course, is the quadrant 1, which is the positive. We know that, though. So for this, I would say that we started here on our trip, and whenever we started, we see that we have a higher point here, but pretending like we don't have that, we could number this, gallons of gas. So say I have a 16-gallon tank of gas. So I could, do 0 here, which is going to be that E, the infamous red E light. And so 0 would go here and 16 would go here. And so I would just number. This is about, a little less than the halfway point. So say it's, 6 gallons in the gas tank, something of that effect. So we weren't quite full whenever we started our trip. So we go, and as we drive, so this would be distance in miles, and this could just go on and on and on and on and on. This graph would end up looking like a big old zigzag. But so say we see here that we've driven some miles at this point. So we start here, and our gas tank becomes empty. So then we move straight up, because we're at a gas station, and so our gas meter, it goes up. But we don't move because we're still at the gas station. So then we again start to drive, and we have a full tank here, or not quite a full tank maybe, depending on your graph, your gallons that your car holds. And then we're driving, and as we drive, the gas, of course, we run out of gas again. So that is why I picked this graph for this one. So we can jump on to the next scenario and see why I picked the next one. So the next scenario given was to explain and label a graph to correlate with the function of the height of an elevator stopping at each floor on the way up. So when I first looked at the all of the different graphs side by side, I looked at this one and I said, man, wouldn't that just be like, imagine you have a stick figure and you're going up, and then you could walk back down, kind of like stairs, right? So that was my first thought of picking this one. And, you know, of course, we've seen all the other ones that kind of have squigglies. So for this scenario, this one felt right for me. So for this, I said it's going to be the time on the elevator is this, the time spent on the elevator, and this is going to be the rise of the elevator or the levels of the elevator. I just said the rise of the elevator. And so for this, you know, we could say that this is floor 1, floor 2, floor 3, floor 4, and so on and so forth. And then this is time, you know, how much time. We've all been in an elevator before. Maybe you have been the child that goes in there and you press all the buttons, you know, on the machine, on the control panel, and then you have to stop at each floor, you know, and then each floor on the way down. So that could be, you know, this scenario here, you know, that we're going to be stopping at each floor. So that is why I picked that one. So this one's kind of fun. It says explain and label a graph to correlate with the function of the height of a bouncing ball dropping from a table. So for this scenario, if I was in a real classroom, I would almost take the students outside and, you know, or in the classroom, I have to be careful of glass and, you know, the windows and stuff, but, you know, let them get hands-on, let them take bouncy balls and drop the ball on the table and, you know, watch it. And what we would find is that whenever we drop that ball, well, first let's label. So I would say again that this is the time that the ball is dropping on the table. So imagine we have a table here, my little table, and we drop the ball on it. So this is going to be, we could say, like the height of the bounce. I think is what I ended up calling it. It's supposed to be a G of the bounce, or the ball bouncing, or, you know, there's no like right or wrong. You know, you just have to do what makes, with this, they're just scenarios. So here's my little table that I make fun of my drawing. So we drop the ball on the table and it bounces. And then it comes back up, but it doesn't have as much momentum, so it doesn't go as high. And then, of course, it bounces again because it's a rubber ball, and it goes on and on and on and on and on, and eventually that little hump, it'll just get smaller and smaller and smaller until it just is dead. You know, it doesn't bounce anymore. So that is why I picked this graph. So this one here was kind of a tricky one for me. The scenario was explain and label a graph to correlate with the function of the length of a shadow of a flagpole length of a shadow throughout a sunny day. What a tongue twister. So through this one, I personally, whenever I did it, I was like, no, that's not it. It should be, you know, the other way around. You know, the actual graphic itself. So what I did is I just used process of elimination, because we'll see on the next one, you know, where it fits. So I knew that this was it. You know, when you're given those scenarios, sometimes you just have to guess, and that's okay. But for this, I ended up finding that whenever I labeled this the time of day, on our x-axis, and on our y-axis, we labeled it the length of the shadow. So for this, you know, I gave us this little flagpole here because I have a little visual to help us. I'm more of a visual person. And again, you know, I love creating activities that students can do in the classroom to kind of get those hands-on, because sometimes it's hard to, you know, think of it all in your mind. So having that hands-on is going to help at least one student. It's completely worth it. So for this, you know, something that we could do was we could actually, you know, track, you know, the actual flagpole outside. You know, every school has a flag, and we all have the sun. So, you know, we could, at different points during the day, you know, we could actually graph this, go out there, we could take pictures, and we could, make a visual graph and show, we could even make like a shadow box, and in the shadow box, have a student put, make their own little flag, and, use a lamp as our sun to show, if we moved it over here and it's 2 o'clock, versus over here and it's nighttime, the different things that we could do. So for this, how it would end up working is, we're going to see that whenever the sun goes here, and I couldn't make my shadow move, but the shadow would actually move to be on the opposite side of where the sun is at. So that's what this graph is showing. So I'll just let my little sun move. So if there was the real sun, then we would see, of course, that the shadow would move to, it would not be on this side anymore, it would now be on the opposite side. So that's why we chose that scenario. So moving right along, what we're going to do is show and explain for g of f of x for, we want to show for x equals 0, 1, 2, and 3. So, what are we even supposed to do here? I really wanted to work this out with everybody so that we saw how to do it, because when we're given this, boy oh boy, it is just very confusing looking. So the trick that I have is anytime that I see f of x, in my mind, I say, you know what, that's y. Let's just call that y. It's a f of x is a fancy way of saying y. So we could say y equals 3x. So we want to find for 0, 1, 2, and 3. So I'm not going to work all of them out, but I am going to work just a couple. So here it is. So we're going to label this 0, 1, 2, and 3. So we are wanting to find for 2 different, formulas here. And what we did, because this looks a little confusing, what we did is we could have 2 charts, and we could label, but they share the same x points, is why we kept them together. You don't have to, but it's just going to save a little bit of space, and there's nothing wrong with that. Later on in the presentation, we'll see that we could actually put multiple on there, and it looks a little scary and confusing at first, but I promise it's not. They just take, unfortunately, a little time to work out. So let's just plug in some numbers. That's literally all we're going to do. So we're going to say y equals, and what we're trying to do is we're trying to find y. So y equals 3, open parentheses, close parentheses, 0. So what is 3 times 0? 0. Anything, And so we're going to do that. Literally, we just plug in the numbers. So what's 3 times 1? 3. And we would do that, so we don't even, do we have to write those? No, we can do that in our head. If you want to write them, that's perfectly fine. But so 3 times 2 is going to be 6, and then 3 times 3 is going to be 9. So that one was pretty simple, but we have to do this side of the chart first, because we see here, see our little f of x, remember what that's called? Y. So we want to take g equals, so we're assigning it another variable. So g equals, g of y equals x plus 8. So what is this wanting us to do? We are wanting to take x, and we're going to plug it in. So the way that we would end up, plugging that in is, so we would say g, open parentheses, f of x, which is our y value, so we plug that in, equals x, which would be 0 again, plus 8. So if we work that out, then we would find that that equals 8, and so on and so forth. We would just continue writing, and we would see that equals 11, 14, and 17. So we weren't asked to graph those, but we absolutely could graph those points. So moving right along. Whew, this one's scary too. So this is going to be, you know, one of those, we took the answers, there they are. So we took the answers, and if we were to graph them, this is what it would look like. We see here that this is all of the points that we just, took, and we see that we have two different lines. So this one here is our blue line, and then this is going to be our orange line. And, we have the same x values. We took our y's, we just plotted the points. That's all we did. So not so scary when it, is on a graph like this. We just took, multiple, so we could even add another, or we could take one away. And it all just depends on, what the question, of course, is asking. So now we're going to visit with a little rise over run. So M equals rise over run. So there's an actual formula that goes along with that, and that formula is y2 minus y1 and x2 minus x1. Again, all we're going to do is take our numbers and we're going to plug them in, and that is going to give us what equals m, which is our slope. Okay, so whenever we do this, this graph, to be honest, kind of confuses me, and this is what I do. And all this graph is, as we saw before, we're given a graph, we plot the points. So these numbers here, we can cross that out because, it's just kind of, it's a sign, so 3, 4, 5. We could have taken that out, but we didn't. We see we're given 2 points. We see their x and y. So what I personally like to do is I like to rewrite them so we know that this is x and this is y, comma, and we could say 3, 1, and then our second point, our second, set of plots, points is going to be 5, whoops, I just can't write today, 5, 5. And for this, and we know again this is x and y values. I really like to label everything whenever I do an equation so that, I don't get confused. I was trying to figure out what I assigned each. So I assigned, of course, this is going to be, I'm going to write on there set 1, and I'm going to call this set 2. Okay, and the reason why you're going to see. So we're going to draw, and we're looking at this here. This is our, our formula that we're going to use to find the rise over run. And I'm going to show you a couple different ways that we can find this rise over run. This is how you're supposed to do it, though. So we see it says y2. Well, what is y2? I see that I have 2 y's and I have 2 x's. But remember here that we wrote set 2. So this is going to be y2. So I put that in here. 5, and I see it's a minus 5 minus y1. Okay, and then I see that I have x2, which is going to be 5 again. It's right here. It's where I'm finding that. Minus 3. So all I have to do now is work the problem. So I see that 5 minus 1 is 4 over 5 minus 3 is 2, and if I simplify that, then I will see that m equals 2. So our rise over run is 2. So what's a way that we can check that? Well, I see here that I have my rise, so that means my up over my over. So my rise over my run. So if we rise up, we're climbing our ladder going up. So let's see how many steps we go. Where's my pen? We go up 1, 2, 3, 4. We go up 4 steps on the ladder, and then we're on top of the roof now. So let's write our rise. 4. Now we're on top of the roof, and how many steps we're going to take? 1, 2 over 2. 4 divided by 2 equals 2. See? Same thing. So our slope here would be 2. That's not so hard, is it? So taking a look at our next one, we're going to determine the slope. So again, we know that the formula that we used just before was y2 minus y1 over x2 minus x1 equals m. M, again, is going to be a fancy way of saying slope. Okay, so let's, not rewrite it. Let's say this is going to be our set, I think I assigned that set, yes, set 1, and this is going to be our set 2. I always like to label it. That's just me. It makes it easier for me to understand. So what we're going to do now, and we're not going to plot it first, okay, because we have these points, and on the one before I already had it plotted for us. Those points I took and put them in. We're not going to do that just yet, okay, because I want to show you how to, of course, work the equation, and then how, if you were to see this, you would just automatically know. So what we're going to do is we're going to, of course, write the equation. So we're going to take our y2 and plug it in. I see that it's a negative. So what do I do whenever I have a negative integer? I'm going to put it in parentheses because it's still negative, okay? So negative 8 minus y1, which is 8. So a negative, and we could work this like this line and then work the next line, because I know that I'm going to end up with another fraction. So negative 8 minus 8 is going to be negative 16. I got to write the 6, Katie. Ooh. Negative 16. Okay, and then our second set, so our x2 is going to be 5 minus 5. Well, so what's 5 minus 5? 0. So automatically, whenever you see this, when you see the 0 on the bottom, we know that it is going to be the slope is undefined. And now we can plot these points, and we're going to see how, and forgive my line, it's probably not going to be very straight, but we see that, you could automatically just see that it's going to be undefined. So whenever we plot points, we see x, so we're going to go over to 5, and then we're going to go up to 8, right here. Okay? And then if we plot the second points, we know that we're going to go over to 5 again, but it's negative, which means we're going to go down. So we're going to go down to negative 8. Now, I could look at that chart and I could automatically know that it's undefined because it shares the same points, but one is just the reciprocal. It's, the opposite number. So forgive my line. It's not too straight, but we always, of course, add the arrows. That shows that it goes on and on and on and on and on forever. But could you see here that there's, of course, a rise, but there's no run. So it's not going anywhere. So if it doesn't have a run, or if it doesn't have a rise, then we know that it's undefined. If it doesn't run anywhere and it doesn't rise anywhere, one or the other, then it's undefined. So that's how we would answer that. But what about this one here? So again, these were just kind of placeholders for our graph, so we could, mark them out. So what we could do, we see these ugly little negative numbers, and they're so scary. So what could we do in this instance? Could we, put it into our slope intercept, formula? Absolutely. That y2 minus y1 all over x2 minus x1, we absolutely could. But what was that other way that I showed us? Is that we could just calculate the rise over run by counting. So in some instances, it's going to be quicker to do that, and that's okay. You know, it's also just another way to check yourself. So this is a small graph, so we can do that. If, you know, the graph went on and on and on and on and on forever, it's probably not going to be very wise to count, you know, every single one. But for this instance, we can. So remember I said that it's going to be rise over run. So our rise is going to be, we are rising up on the ladder. We're walking up the ladder. Okay, so let's count that. We go through 1, 2, 3, 4. So our rise goes on the top right here. We see that. So it's going to be 4 over. And our run, we go 1, 2, 3. 3. So our rise over run would be 4/3. Yeah, 4 over 3, which would simplify to saying that our slope is 3. All right, so moving on to the next one. Whew, this looks scary. So before we took and, you know, we of course plugged in those numbers, and you know, we saw that. Again, all we're going to do, and we could work this absolutely, but, you know, for time efficiency purposes, we're not going to do that. We see here that we have 3 different blue colors. And what we do is we, of course, have the same x values here for all 3 of our formulas given, our equations given. And we just plug that in. So we say y equals x. So in this case, our x would be -3. So y equals -3 square root of 2. And what we would do is we would just plug each of those in, and we would find each of, you know, the y values. And then we go on to the next one. So we have half of the work done for us at this point, because we see here that it says y squared, so y up caret 2, and that's the same thing as this. So all it wants us to do is add 7. So half of the work for this equation is done. We just have to add 7. So that's how we got each of these numbers. And then again, this third equation that we're given, it's the exact same, except this time it says it wants us to subtract 7. So by doing this and having them side by side, something that you may not have, you know, recognized before is that they are all very similar. And by knowing that they're very similar, you could have guessed that, you know, this could be your chart. You know, if you were given all of the charts, you know, side by side, you know, you could have guessed that this would be, of course, a parabola. So moving on to the next one. Boy, this one looks scary as well. So what we're going to do is we're going to put this into what's called y equals mx plus b. Let me write that for us up here so we know. So this right here is going to be our y equals mx plus b. So what we're going to do with that is, of course, plug in those numbers. We see that we're given some numbers here, and those numbers are shown right here. And what those numbers are, let's see my y here, we see that's where they meet. So what we're going to do is we're going to put them into this form here, which is, we see that our original slope is -3/4 right here. And we see, of course, yes, that we, of course, have a perpendicular line. Just by looking, we see that. But what we're going to do is we're going to take this and we're going to put it into y minus y1 equals mx minus x1, and that's going to give us m equals, so slope equals 4/3. So what that is, this is called a reciprocal, and anytime that we see 2 slopes, where one is a negative and one is a positive, we know that we're going to have what's called a perpendicular line. So now that we have, of course, our new slope, all we're going to do is we're going to plug in those numbers to find our new points. And if we were to plot these points, this is, of course, is what our graph would end up looking like. And we know that that's, of course, perpendicular lines. So, very similar question. Again, we're going to do essentially the same thing. Plug those in. We see that the original slope was -9/2. We see that the reciprocal of that is 2/9. Whenever we type these in, they look a little strange, but it's the same thing as saying 9/2, just like that, and 2/9. So we see here with our reciprocal that we flipped it and we changed the sign. So again, with that, all we would do is, of course, work the equations, plot the points, and we see again that we have perpendicular lines. So this one is kind of fun. We'll see whenever we graph it what it looks like. So what we do is we are looking for the equations of tangent lines. So we know that the radius is 9 at 0, our point here is 0, -9. So we see here that we have these, points plotted, and we know right here is the middle of our circle, which is 0, 0. If we were to connect all of these points, we would see that we have a circle. So as I stated over here, from 0 it goes over 9, and it goes up 9, and over this way 9, and it also goes down 9. So we could say that our radius, of course, is 9. So we could plug those points in, and that's how we would get them. So moving along, though, we see that if we were to plot the points, then we would see that we have what's called a tangent line. And so a tangent line, it's a straight line that touches a curve at one point, and at that point where it meets, it has they share the same slope in that moment, but that moment only. So we could say that, they're going the same place, but they only meet at that one time. Looking at these here, though, we see that we have this line here, this black one, and this black line here. We know that that is what's called parallel lines. So, if we were to take these two, away, and we were to plot them here, we would see, of course, that we have, if we were to move our tangent lines and just, rotate this entire graph, then we would see that we could share, of course, parallel lines in that way as well. So I think that that's all that I have today, guys. Thanks so much for watching, and I'll see y'all next time.